Now that we've generated polygons based on our levels, and we've run through a convex decomposition algorithm or a triangulation algorithm on them, now we need to go through the next steps of generating graph information on those spaces. So this is a relatively straightforward process. If we have a series of triangles like this, right, we can generate the graph data based on shared edges, right? We can generate our graph data based on shared edges. There are 3 triangles here, so we could represent our graph with nodes at the center of each of those triangles, right? Remember that really our nodes in this case for our graph aren't actually small points like this. Really what they represent are 3 different triangles. So here, let me pick a different color. So this is one of our nodes, this triangle. This is one of our nodes, this triangle. And then this is one of our nodes, the triangle down here, right? These nodes are not single spaces like we typically think of with graphs. The next thing that we need to do is figure out what our edges are. Our edges between each of the graph elements would be any shared edges between the 2 triangles. Here is an edge of our graph, and here is an edge of our graph. This is a graph drawn using nodes and edges very simply. That would look something like this. It's just 3 nodes and 2 connecting edges between them, right? This process for generating the graph data, generating the underlying graph data, can be relatively simple or relatively complex depending on how you've done triangulation and polygon generation. It's my recommendation to use the idea of a half-edge data structure. A half-edge data structure, which is commonly used for a lot of computational geometry or 2D complex geometry like this, is the idea of representing edges of polygons as if they're only half of an edge. I'll tell you what that means. If I have 2 adjacent triangles like this that share an edge, let's zoom in really close at what this edge would look like. This would look like, here is one triangle like this, and then here is a second triangle right here, and these share this edge. Using this idea of a half-edge data structure, these edges would essentially, or these half edges would essentially hold a few different things. Each half edge, so if I just wrote this out as like a small class, each half edge has 2 vertices. Here's a start vertice and an end vertice for this edge here. And then here is a start vertice and an end vertice for this edge here, right? So there's 2 instances of this class, 2 instances of this data structure, each representing 1/2 of this edge. This half of the edge that corresponds with the bottom triangle here has the start point of A, right? I'll represent this as position A and position B. Half edge has a start position, which we would probably use a vector 3 or probably even a vector 2 because these are just 2D polygons, but they'll have a start position, it'll have an end position or vertice, right? And then the other thing that it would have is also a reference to another half edge. And you can call this the other side or adjacent. This reference here to the other half edge, on this edge, it would store a reference to the opposite edge. On the top edge, it would store a reference to the bottom half edge. This data structure, and the reason why it is built like this, is so that as you are writing your algorithms that sort of do your ear cutting methods or your triangulation or any of your other geometry type methods, as you are traversing around an individual polygon, it's very easy to hop over to this polygon and look at this side of the edge to continue doing logic there, right? So this is the reason why we use this half-edge data structure. Otherwise, you end up doing a lot of sort of traversal around your various points to figure out which edges are overlapping and so on and so forth. If you use a half-edge data structure like this, when you are generating and storing all of your polygons, this half-edge adjacent gives you the knowledge that you need to be able to create these connections here in your graph. Everywhere where there is an adjacent half edge, that is a graph connection. Here's a graph connection right here between these two polygons. This edge would have a null value for its half edge. This edge would have a null value for its half edge. So there's no connection here, no connection here. Same with these. There'd be no connection here and no connection there. So very easily with this half-edge data structure, using this to represent our polygons, we can pretty quickly generate our graph data structure that we need in order to do pathfinding over these polygons.